Yeah, we start the past of introduction some kind of brands for industrial robots manufacturing in the world. And today we will continue with the robot configurations. And as you know, that configurations is maybe the will be design depends on the tasks of the robots, and some kind of robots it can be classified according to this kind of configurations. For example, this might be Cartesian, cylindrical, or spherical, or articulated, or scalar robots. There's some kind of classifications based on the configurations, and we have some terminologies for the robots. For example, the first one with the positions. The positions it can be the translational location of some things, and the orientation. The orientation is defined as a rotational angle location of something. So a robot's orientation is measured by the roll pitch jaw angles. And the link. The link is a rigid piece of materials connecting joints in a robot. And how about the joist? The joist is a device which allows relative motion between two links in a robot. And there's some main definition that we work with the field of the robot. And beyond that, we will have some kind of configurations as follows. The first one is Cartesian, or we call the rectangular gantries. With this kind of configuration, the robots are made by three linear joints that orient the end effectors. It's usually followed by additional revolution joints. And this guy is one of the most common used for the natural robots. As you can see here in the fingers, we have the movement according to the Cartesian coordinates, X, Y, and Z. And it's connected with the end effector of the robot, and later we call it wrist. And the next one with cylindricals. With this kind of configuration, the robots will have two primitive joints and one revolution joint. The third one is spherical joints. With this kind of robot configuration, it will follow a spherical coordinate system that has one is primitive joint and 2 rotational movements. The next is articulated robot, and with these configurations, all joints are revolute. It looks like a human arm, and we can see here in the fingers. This is the first one. It's a rotation movement, and the second, and here's the touch. And this case is famous for the name of SCARA. Yeah. SCARA is stand for the Selective Compliant Robot Arm. It includes 2 rotations and 1 rheumatic joint. And here we have 2 revolute joints and parallels. So it can have about 4 and the touch joints can have to move and to reach the target. So we have a definition of reference frames. It's divided into the one reference frame. The one reference frame, which is an universal coordinate frame, and it can be defined as the x, y, and z axis. And in this case, the joints of the robot moves simultaneously and to create the motion along the 3 major axes. Another reference frame is called the joint reference frame, which is used to specify the movements of each individual joint of the robot. And in this case, we have the joints may be accessed individually. And for this case, one joint can move at a time. The third reference frame is a tool reference frame, which specifies the movement of the robot's hand related to the frame attached to the hand. So we have 3 axes, X, Y, and Z attached to the hand that define the motion of the hand in relation to the local frame. So all joints of the robots will move simultaneously to create the coordinate motion about the tool frame. And the trees have reference frame. This can be used for the control of the robots. And by using the handy control, and you can select one of three different frames and to help the robots to move. And here is an illustration for the frame. With the first one, we have the X, Y, and Z is a one reference frame. And according to this, the end effector of the robot will move according to the three directions as we set up for the X, Y, and Z. And the second one is the rotational movement of each joint. So we can move one by one. And the third one is the tool reference frame that we define for the robots and effector. And according to the three directions and all the link and joints of the robots need to move simultaneously to make the end effector can move according to the direction of each axis of the end effectors. And the work envelopes that's created by the movements of each axis. So it depends on the configuration and the size of the link and the wrist joints. So the work envelopes of each robot may be different. And the robots can reach to a collection of points, and we call the workspace. So in order to know how the workspace is, maybe we can move each joint through its drain of motion. Actually, maybe in literature field, we have different range in comparison to the practical one. And combining all space of each motion can reach, and we subtract what space is cannot reach, and we can find that the workspace of a robot. So for the first kind of configuration, and you see here, according to the movement of the X, Y, and Z, and we create the configurations of the workspace. Here is shape, and according to the movements of the end effectors, here is the grid that's attached to the end effectors. So we can also create a small workspace And totally we can create the overall workspace of this kind of robots. And here is the finger show you in different views. And belong to the movement of each axis. And we can create the areas. So this maybe belong to the traverse strokes of each link. For example, here you can see that these areas is created by the horizontal movement and the vertical movement. And how about this? From figure the three creates or your shape was this kind of robots. What is shape? Can anyone tell this or tell us about this? And you notice with the cutter configuration, and we have a rectangular space for the workspace. And how about this?
These are cylindrical.
And it's a solid one or
A hollow one.
okay. Yeah, of course, because we have to subtract the areas that the movements of the joints and links cannot reach. So of course it's a hollow cylinder ones, okay? And here you can see this. With this view, we can create an areas of the horizontal movement and the vertical And here is the top views, and you can see that's the areas by the movements of the joints, and it's the range of the angles movement. Okay, so all the limitations destroy, and we create the shape. That's created by the two circles, and we have, and with the verticals sharp, and you can see that we can create this kind of shape. And next one is articulated. And with this kind of configuration, and we have three rotational movement with three revolutions and do the same, and we will create the workspace. But with that kind of movement, maybe some areas when create and we need to subtract that some area that this editor cannot move. And also similar to the Scala robot. And now with articulated one, with 6 degrees of freedom, and we have two kind of robots. First, we need to clarify about each movement of these kind of robots, and after that, you can draw the workspace of these kind of robots. Here's freedom. The first one is
We cannot hear anything, sir.
and the second, this is the third one.
Sorry, sir. We cannot hear anything.
Yeah. Okay. Yeah, I hear someone have any problem or questions.
Your microphone is disrupted.
Oh, right. Yeah, I also get a notification about the hey gang. Can you hear me? Hello? Can anyone hear me?
Yes.
Sorry. Hello?
Yes, sir.
Yeah, it is still okay. Hello, guys. Can you hear me?
Yes, sir.
Oh, sorry. Okay. So, guys, can you hear me now? Okay.
Yes, sir.
Yes, sir.
Okay. So we have the configurations of the KUKA robots or the ABB robots. So this kind of robot has
Hospital, traffic accidents are the worst.
oh,
Thank for food. Food.
So I hear this great signal from someone.
That I do this work that's not so dangerous. Most accidents. Oh,
Sorry,
I lost count the number of times.
right. Do you have any questions? So with other guy, can you hear me clearly? Okay.
Yes, sir.
Okay. So let's continue. Yeah. Now we have a small exercise for you. That's first we have two cab robots as the same, quite similar, but a little bit different in the configurations. The first one is KUKA 300 and the second is ABB 140. So first, from this kind of configuration, we have to find out its workspace. So in order to make it clear, I will show you the 6 degrees of freedom of this kind of robots and how it works. And I'll find the information about this kind of robots, or you don't need to really to find the detailed information, but according to the degree of freedom of this kind of robots, and you will max out and to find out the workspace of this kind of robots. Okay, so I'm afraid that the degree of freedoms of this kind of configurations, the signal is not good, so I will repeat it. Okay. And here I show is can you see this figure? Okay.
Yes, sir.
And with this one, we have the first revolution choice as this, and we have the first. The second is here, and here the third one. And how about the fourth? The fourth is this one. This is revolution choice, and we have this. And the fifth, this one. And the last one is will attack to the any fixture of the robot. And you can see theta 1, theta 2, theta 3, and theta 4, and theta 5, and theta 6. And based on this movement, from this movement, and now you will find the workspace of this kind of robot. And map out the papers, and after that take picture and send to the chat, and we can see the results of some of you. Okay. So anyone has the results? Trung Việt, are you there?
Yes, sir.
Have you finished your work?
Not yet, sir.
Yeah, with this kind of workspace, normally we draw according to the two kind of views, from the top views and from the rear views or front view. It depends on views. So anyone finish or not yet? Okay, so how many links do you have?
Two.
Yeah, we have 6 drawers. Yeah, it's of course it's similar to this, but I would like to know in details too. Make it more clear. And please pay attention to the range of each angles. And how about others? Yeah, show me your work. Any other results? Yeah, great. Yeah, now you should draw by yourself, and I will show you the result, and we will make the comparisons. And from that, you will have some ideas for your own about your work. Yeah, it's better that than you only found the results from somewhere and show here. Maybe our robots were a little bit different. For example, in the previous ones with the churn work, right?
Yes.
Yeah, and how about others? No? Sorry, only one guy's work in our class. How about other members? Lê Đức Toàn, have you finished? Việt Anh?
I'm here.
Yeah, and how about the work? Can you show us?
I'm sorry, sir. I am not finished yet.
Why not? Yeah, try and show me your progress now.
Sorry, just give me a minute.
Okay, yeah. Okay, so Oli Chung has an average one. And other guys. Okay, from Josh's answer, so we have some discussions. How can you do this? Minh Trương?
I have just imagined, and I guess the motion of the sword.
Okay, so do you have you work on the computer, right?
No, no, sir. I
No?
just get by my mind.
I mean that you study this course through the website and use your own computer, right? Or smartphone?
As the smartphone.
Smartphone, okay. Yes, actually, to do this, first, you should find the information about the KUKA robots. Yeah, from this model. For example, you will find a PDF file that will show you the most important thing here is the angle range of each joint. And from that, you can draw. Unfortunately, here you already draw these areas, and we see this. This is one of the models which appear very choice and we can draw this, but this one is very common. It's the same maybe for all kind of their articulations, configuration, and this area is subtracted from the area that the effector cannot reach. But for the KUKA robot, you can see it's a little bit different. This is for the ABB. And for the KUKA robots, let me show you that it's easier for you to find out the results. For example, here's according to one member in our class, and from my point of view, you can find out the KUKA robots 300 information. Yeah, here you can see that we have some curve. So I use this one. Let's see. The network signals today is My home is not really good. Yeah, here. First, you can see that's the information about the range of each motions. With A1, A2, A3, A4, A5, and 6, according to the angle of each joint. And from this, you will map out the top one's areas and this one. See? Yeah, can you see this? The detail area that's mapped out by all the links and joint movements of the robots. It can be mapped out here. And of course, it also includes an areas of the an effector that can be attached that we can call the extend through areas outside. Yeah. This means the reachable workspace. And it's not only in the front, but also in the back areas. Okay, so that is for the workspace. And based on this workspace, after you map out the workspace, and it can give you some ideas about the control. If the robots can reach that area or that position or not, or how it's moved. And based on that, maybe when you use this pendant, and it's easier for you for choosing the control methods. And I told you about the wrist of the robots. It's similar to our hands. It typically has 3 degrees of freedom, and we call with the roll pitch jaws movement. The rolls evolves to the rotations of wrist about the arm axis. And in the previous example of the KUKA robots, and as the force movement. And pitch is the up and down rotation, and jaws is the left and right. So with this kind of movement, you can hear, and maybe in some other courses, the end effector is mounted on the grid. And here you can see that the features with 3 types: rolls, pitch, and rolls. Yeah. So the first one, you can see this. Yeah. This one. And the second, this one. And the third one with this. The end effectors is attached to the last links of the robot. It can be the tool, grippers, or other device. It depends on the task that we would like to give the robots or the manipulators. So maybe with some kind of robots, it can be attacked with a fixed one, and the others is mounted with a flexible one. Actually, the end effector can be divided into two kinds. One is gripper and the other is tool. The grippers may be used for grab and hold an object and pick it and place it as a desired position. So, about the grippers, we may have the mechanical grippers or the vacuum or suction cup or magnetic gripper or adhesive grippers. Others may be the whole screws and its surrounds. It depends on the task or the detail of the specific case. And tools. Maybe the tool can help the robot to perform an operation on a workspace. For example, with the welding, we have sports welding or the arc welding. So it can be the sports welding tools or the arc welding tools, or sprays, paintings, or rotating spirals for drillings or grindings. So these all are the methods that can help the robots for its work. The power sources of robots. One of the important elements of the robots is the drive system. It supplies the powers and makes the robots unable to move. The dynamic performance of robots mainly depends on the type of power source. So maybe it belongs to the task that we give the robots, and after that we make calculations and choose the suitable power sources for the robot. First type is the hydraulic drive. With hydraulic drivers, it will provide with fast movement and with large powers, so it can help to move the heavy parts. But the problem is we need the hydraulic resources system. So it will occupy a large space areas. And another thing is, of course, with these kinds of source, the noise is also a problem. And another one is the environment, because there will have dangers of the oil leach. So it will become a problem for long use this kind of drive. But it can help you to use in some dangerous areas, for example, in explosive environments. We need very strong powers to work with the heavy duties. The second one is electric drive. This kind of drive maybe a little bit slower movement in comparison to the hydraulic robots, but it has the advantage of the size. It maybe only requires small size of the working areas for the drive. So it's suitable for small and medium-sized robots. And another thing is, it can have to get a better positioning accuracies and repeatabilities. And with electric drive, it can be step motor or the DC motor or the AC motors. With the stepper motors, we can apply the open loop control. And for the DC and AC, it can be the closed loop control. Of course, with these kinds of drives, the noise is reduced and a cleaner environment. So that's why now it is the most popular drive in industries. The third one is the pneumatic drive. This one is preferred for the smaller robots because it's cheaper, but the powers is not so high. So it is suitable for a relatively less degree of freedom design. It means that it's suitable for the simple tasks. For example, with the fixed and place application. And actually, in our school lab, in industrials robots application, we have hammer robots, and it's applied this kind of drives. And for KUKA robots, it's applied for the electric drive. So here we also have some other terminologies for the robots. The first one is a speed. The speed can be defined as amount of distance per unit time at which the robots can move, and usually specified in a second or the meters per second. And the speed is usually specified as a specific loss, or assuming that the robot is carrying with a fixed weight. The actual speed may vary. It depends on the weight carried by the robot. And this definition is popular within the field of the physics, right? And another one is the load-bearing capacities. It can be considered as the maximum weight carrying capacity of the robot. The robot that carries the large weight but must still be precise as very expensive. We would like the robots to work properly. It means that it has assure with the powers and the speed and precision. These two criteria seem to be conflicts. Because it related to the two kinds of problem. The first one is a speed. The second is stability of the system or the robot configuration. And these two characteristics, how can we find out the optimum values is a problem. Because the speed it defines how quickly a robot is. But the stabilities refer to the robot's motion with least amount of oscillations. And a good robot is one that can fast enough, but at the same time it has a good stability. So solving the problem and find out the relation between two of these characteristics of the robot is a problem for the engineer and for the one to solve or work with the robot. Because the two roles are conflicts. And a good controlling system, it means that it can be designed for the robots to facilitate a good trade-off between the two parameters. And the precision of a robot's movement is defined by three basic features. The first one is the spatial resolution. It is the smallest increments of movement into which a robot can divide its work volume. And this depends on the system control resolutions and the robot's mechanical inaccuracies. Second one is accuracy. Accuracy can be defined as the abilities that a robot to person its grip and as a desired target point within its reach. Or it can be considered as abilities of a robot to go to a specific locations without making any mistakes. So in terms of the control resolution, the accuracies can be defined as one type of the control resolutions. And we have a problem. Maybe in the worst case, when the target point is between two control points. The reason is that displacement smaller than one basic control resolution unit. And we call it a BCRUs. This can be neither program or noise measures. And on average, it accounts for 1/2 of BCRUs. Actually, it's impossible to position a machine exactly. So from that reasons, the accuracies is defined as abilities of robot to position itself to the desired locations in a minimal errors. And for the industrial robots, it's normally 25 millimeters. Cost in the past, and we can see that the accuracies of a robot is affected by many factors. And you can imagine it's quite similar to your arm. And similar to the robot manipulators. If your arm is fully stretched out, maybe the robot's structure is also the same with the mechanical inaccuracies will increase because the loss tends to cause the deflection. And the third one is the definition of the repeatability. This can be defined as abilities of a robot to repeat the portion itself when asked to perform the same task for many times. Or we can define as abilities of a robot to position the end effector to the previous position location. So here, you will need to clarify between the accuracy definition and repeatability definition. Accuracies can be considered as an absolute concept, and repeatability is a relative one. Maybe a robot can be repeat turbos, not very accurate, and vice versa. And I will show you the relation between the accuracies and repeatabilities. From the first picture, finger here, you can see that this one is repeatability, and accuracies is absolute value, so it's big and small. So with this case, how about the accuracies? And how about the repeatabilities? Low accuracies and also low repeatabilities. And how about this one? Repeatabilities and accuracies are all in the small circle. So we can see here is the high accuracies and high repeatabilities. And how about this one? How about this one?
Low accuracy, high repeat ability.
Yeah, okay. And how about this?
High accuracy, repeatability less than the previous two.
Yeah, two previous case, right?
Yeah.
Okay. And how about this?
Both are worse. Repeat and accuracy or bad.
So which ones are the best one?
The first one in the 4.
This one, right?
Yeah.
Okay, yeah. So that is our goals of the control. But it's quite difficult to get the package. Okay, so maybe today we will stop here and we will continue next week. Any questions?
Can you upload the slide?
I haven't uploaded slide. Okay, sorry. Yeah, okay. After class, I will upload the PT file for you. Okay.
Yeah, thank you. Yes, thank you.
Okay. So, no more. Okay. So if there's nothing more, so we will stop here. See you guys.
Thank you, sir. See you next week.
Okay. Have a good weekend.